Okay, so fresh off of a growth model, now let's take a look at a decay model. And the good news is the work is very similar because the functions are very similar. So recall from our groundwork, the function is f of t equals a to the e kt, but in this case, k is a negative number, right, which causes the decay, exponential decay. Again, a is the initial amount, so that also works like your y-intercept. K is something that's either given to me. Again, it's usually a percent, all right, but it's usually given, or it's something we have to find by using some other data point that's given us, some other x, y, and we'll investigate that in the near future, because right now, right, for the example I give you, I actually give you the function. So the function q of t equals 32 e to the negative 0.002 t mathematically models the quantity in grams of a particular radioactive isotope in terms of T. Use this model to do the following, right? So again, is this a growth or decay model? What's decay? Because we're talking about decay, but the real reason is there's your K value right there. K is negative 0.002, and it's less than 0, right? So that's a classic situation where we are a decay model, right? Especially since E's, our base is greater than 1. So it is decay. As a matter of fact, if you wanted to work percent-wise, right, we're going at 0.2%, right, is how much of this radioactive isotope is moving away. What is the initial quantity? Well, again, we're looking at the number sitting right in front of everything. Of course, if you weren't sure of that, you can plug a 0 in there and convince yourself yet again that that's true. So if I plug 0 into the function, I get 32 e to the 0. Of course, anything to the 0 power is 1, and we get 32. So hopefully you'll just start memorizing the fact that that number sitting right in front of that exponential part, that is your y-intercept. That is your a value. So you can do it by inspection, but there's the actual mathematical work y. How much of the isotope is left after 20 years? Well, in this case, t is equal to 20. And so we just basically evaluate what's the function value at 20. So plugging that in, we get 32 e to the negative 0.00 t times 20. And I'm just going to go ahead and put it in the calculator and in that juncture. So we get 32. Oops, let me just make sure it's on. 32, and I got my exponent, and it's being raised to the negative 0.002 times 20. And I think I got all the action right there. All right, and so when I press enter, it looks like we get 30 point, let's just call that 75. We'll go out a couple decimals. So 30.75, and this would be in grams. Okay, so after 20 years, no matter where we started, right, there'd be 30.75 grams left of this particular material based off of the model that we were given. All right, so our next move then, they're changing things up, or I'm changing things up. I'm asking when will there be 5 grams of the material left? So functionally speaking, I'm not giving you an input. I'm telling you the output is 5. All right, and so for this model, we have our model 32 e to the negative 0.002 t is equal to 5. And so we basically have to solve for that t, and we do that using the same thing we've been doing since 6.6 or heck even 6.3. I'll begin by dividing by 32. So that gives us e to the negative 0.002 t equals 5/32. To get to that t value up in the exponent, I'll apply a natural log to both sides. Again, the reason I chose a natural log is they're inverses, so those clear out, and we're left with that and that fraction there. Divide both sides by negative 0.002, and there's your t value, right? So t in exact terms is a natural log of 5/32, negative 0.002. But in terms of an actual value, right? Not an exact, but a decimal answer to give me a feel for what that is. We just punch it in the way it looks. So I got the natural log of 5 divided by 32. Close those parentheses up. Divide this by a negative 0.002. And what I get is 928 0.1, how about we say 5? Okay, so to get down to, how about this? We started with 32 grams. To go down to 5 grams, it's going to take 928.15 years to get there, again, based off of that model. So pretty long time. What's a little depressing is most of your very radioactive material, the waste that we make, their half-lives are even longer than that. So they go in like in the thousands of years. But the good news is things like carbon dating, right? Carbon has a very long half-life, and that's why we use carbon dating to date bones and kind of do some fun stuff with it. Okay, which leads us to what's famously known as a half-life. What a half-life is the time that it takes to reach half of your value. And it could be your original value if you want, right? But the half-life, it's the same no matter where I start. So in this case, we're starting with 32 grams. So half of 32, right, is 16. So to find the half-life of the isotope, in this case, we're just basically asking, when does my Q of T equal 16? And so we basically follow the math we did in part D. So I take my function, and I set it equal to 16. Divide both sides by 32 first, and lo and behold, what we get is e to the negative 0.002t equals 1/2. Applying a natural log to both sides, we get negative 0.002t equals the natural log of 1/2. Divide by that, and we get our half-life value, the amount of negative 0.002. That's a negative there. So t is equal to that natural log of 1/2, negative 0.02. All right, after I made a train wreck of it. So again, reaching for our calculator, plugging that in, we have the natural log of 1 divided by 2, and then we're dividing that by negative 0.002. So this half-life is 346, let's say 57. So 346, 57 years. Alright, so again, no matter how much material I have, whether I start with 32 or 10 or 5, right? If I had 5 grams, the amount of time it takes to reach 2.5 grams would be 346, 57 years. So that is what a half-life is. Take the amount that you currently have, the amount of time that it takes to reach exactly half of that. And that is how we basically do that. It does turn out, since it is a half-life, usually what your half-life is the natural log of 1/2 divided by whatever that k value is in your function. So it's actually a formula you can look up, but hopefully you can see it just being built in the math itself. So there's your decay model. What's nice about what I've done so far is we've introduced ourselves to the exponential models, and then I have actually given you the equation. But what happens if we don't have the equation, but we still have to build a model, right? And that is coming up in some videos coming soon.